the assumption Einstein needed, one-way versus two-way light. To see why the instant that isn't keeps getting away with it, we have to open the box almost nobody touches. There are two speeds of light hiding inside one symbol. The two-way speed, the out and back you get from a ping and a reflection, is what we actually measure. The one-way speed, the straight shot from A to B, is what we assume when we set clocks. That move wasn't a loophole, it was Einstein's genius. It's also the seam the story keeps snagging on. In 1905, Einstein needed a clean way to glue distant events into a single timeline. He proposed a rule that feels obvious until you look closely. Synchronize clocks by sending a light pulse from A to B and back. Then set the clock so that the travel time is split evenly between the outbound and inbound legs. If the round trip takes t, you declare the one-way times t2 and t2. That choice, Einstein's synchronization, bakes in that the one-way speed equals the measured two-way speed, c, in all directions. Philosophers later gave that choice a dial. Hans Reichenbach introduced epsilon, a parameter that tells you how to split the round trip. Epsilon equals 1-2 gives Einstein's symmetric split. Tilt epsilon away from 1-2 and you skew simultaneous in a direction-dependent way, while keeping the same round-trip c and the same local physics. If you rewrite all your equations consistently, observables tied to round trips don't change. You get the same experiment, the same radar distance, the same Doppler tracking. The world doesn't move, the bookkeeping does. Why should anyone care? Because our hardest problems ride on clocks. GPS works by comparing one-way signal times from satellites to a receiver down here. But under the hood, it's built to cancel the traps. It solves for receiver time bias, uses relativistic models for satellite clocks, and relies on a constellation tied to a global coordinate time defined by Einstein synchronization. Time transfer between national labs, fiber links, and satellite common view all inherit that same convention. It's not wrong. It's a standard. Standards are how the world functions, but standards are also choices. Here's the stakes in practice. Every time you call two detections simultaneous, you've already picked a way to align the tapes. Entanglement experiments trust picosecond time tags that were disciplined by a network using Einstein's rule. Neutrino burst comparisons between continents translate local times through GPS and geodesy into a world clock that assumes symmetric one-way light. Deep space navigation lives on two-way tracking, but when you cross-compare stations or fold in one-way ranging and time transfer, you step onto the same convention. Our universe of data is stitched together on a principle we chose because it makes the math sing and the missions fly. The predictable objection is right and misleading at the same time. If epsilon is just a convention, then nothing physical depends on it. True for round-trip observables, true for any local lab in free fall. But the interpretation of distant order, the sequence you write into the script when you say event A happened before event B across the sky, leans on the slice you picked. Special relativity tells you not to treat distant simultaneity as a fact of nature, it's coordination. Einstein's move made that coordination simple and isotropic. That simplicity feels like truth because it works everywhere we've looked. Metrologists live in this world daily. They fight picoseconds of dispersion in fibers. Forward and backward paths aren't identical. They calibrate two-way satellite time and frequency transfer to nanoseconds, while one-way delays soak up models of troposphere and ionosphere that don't perfectly mirror. In their notebooks, you'll find lines like assume symmetry to first order, residual asymmetry below XPS. It's honest, and it keeps the trains on time. It also marks the seam. We can measure the out and back. We can only define the straight shot. Human moments make the point stick. In a timing lab, two hydrogen masers sit like quiet metronomes. A technician routes a 10 MHz reference through kilometers of buried fiber and discovers the forward path lags the return by a hair. A colleague adds a dispersion compensator and writes assume symmetry in the log. They both know that assumption is the move that keeps the network sane. it's also where reality leans on a promise we make to ourselves. Now tie this back to the threads we've been pulling. SN 1987A's neutrinos beat the light not by breaking C, but by leaving first and traveling differently. To compare arrivals, we mapped local clocks into a global time by Einstein's rule. The story holds because supernova physics and good synchronization agree. Pioneer's Doppler residuals were a two-way triumph, translating them into where the probe is right now, folds in Earth orientation, station locations, media delays, and the same synchronization underneath. Quantum Bell tests sort coincidences by time tags disciplined under that convention and overlay light cones drawn with a C we know from round trips. None of this undermines relativity. It strengthens it by making the contract explicit. The invariant content, the stuff no coordinate choice can touch, is built from local measurements and round trips. The seductive content, now across the galaxy, instant coordination, earlier by hours, rides on how we chose to set distant clocks. That's the glitch worth naming, not a broken wall, a seam. The speed of light is a hard budget for messages you can control. The one-way value that lets you line up distant tapes is a definition that has never betrayed us, and might never, but remains a definition. There's a reason textbooks keep this in the basement. In careful hands, it's unexciting. Change epsilon everywhere and you get the same answers. In clumsy hands, it sounds like license to say anything. We're not throwing a party for ambiguity. We're putting a label on the contract we signed in 1905 so we can recognize it when anomalies press on the edges. Because the next arenas, horizons that look like render boundaries and vacuums that aren't empty, depend on how the budget is enforced, not on breaking it. The wall as a refresh rate, computational universe framing. So here's the turn that makes the seam useful. Stop treating C like a moody traffic cop and start seeing it like a system budget, bandwidth, latency, throughput. If reality computes, limits aren't proclamations, they're resource ceilings. Blow the budget and frames tear. Stay inside it and everything looks smooth enough to call law. Stakes first. A budget can be optimized. That's where routing around cost becomes a plan instead of a prayer. There's a lineage here. In the 196s, Rolf Landor nailed information to thermodynamics. Erase 1 bit, pay at least kT ln2 in heat. Information isn't ink. It leaves a thermal footprint. In the 199s, Norman Margolis and Lev Levitin linked energy to the maximum rate of orthogonal state transitions, roughly 2 EH operations per second. Give a system energy E, and there's a cap on how fast it can genuinely move to a distinguishable state. Those two together whisper a picture. If every finite region has finite energy and entropy, there's a ceiling on update speed and memory. The light cone starts to look like a dependency graph enforced by a global tick budget. Translate that into familiar physics without pretending there's a literal CPU. Fields update locally. Interactions propagate at finite speed. Lorentz symmetry is the compiler that keeps the code consistent. In that reading, C is the width of the bus connecting causally related updates. The front velocity that guards causality is the hard cap on when a controllable change can first appear. Anything that looks faster, phase velocity games, group velocity tricks, entanglements, instant-looking patterns, isn't a violation. It's caching, pre-computation, or compression showing through. Skeptics hear simulation and reach for a red pen. That's not required. Seth Lloyd's universe as quantum computer, Stephen Wolfram's rewriting systems, and Leonard Susskind's complexity as length aren't claims about teenagers rendering galaxies. They're claims that the laws we already trust are best understood as constraints on information processing. General relativity plus quantum field theory already enforce causal structure and finite signal speed. The computational framing is a different pair of glasses for the same scene. It highlights budgets and trade-offs you can exploit without changing the math that works. Human moments make it real. In a seminar room, someone writes KTLN2 beside a sketch of a black hole horizon and says, "Erase here, pay there." A colleague circles 2EH and quips, "So that's the overtime policy." A grad student draws a light cone and writes dependency DAG, then grins because the joke landed in a room that shouldn't find it funny. What matters is the shared instinct. Limits are resources. Resources can be scheduled. Now put gravity into the conversation. Black holes carry entropy proportional to their horizon area. The Bekenstein bound caps the information in a region by its energy and size. Holography says bulk physics can be encoded on a boundary. Susskind and collaborators go further. The interior volume behind a horizon seems to track the quantum complexity of the boundary state, the minimal number of simple gates needed to build it. Complexity, in that sense, acts like an internal clock. It grows linearly for a long time, pacing what the interior can do without any superluminal courier. The refresh budget is enforced both locally by C and globally by how hard it is to rewrite the state. That reframes our earlier seams. Entanglement's instant isn't a courier sprinting outside the cone. It's precompiled constraint across a shared state that only becomes actionable when a classical note arrives at light speed. SN 1987, A staggered messengers look like channels with different buffering and access rules. Neutrinos punching out on a low-latency path. Photons waiting for a congested surface to clear gravitational waves. Had we caught them then? Radiating straight from quadrupole dynamics. Pioneer's Doppler saga becomes a parable about reading a compiled interface, two-way timing, while forgetting you don't see the source code, the one-way path you define by convention. If C is the refresh rate, where do glitches hide? Near render boundaries, horizons, strong curvature, places where the scheduler runs hot. That's where thermodynamic analogies stop being analogies. Hawking radiation isn't a metaphor. It's a budget reconciliation between field fluctuations and gravity's bookkeeping. Islands and entanglement wedges aren't literary flourishes. They're instructions for where the code that reconstructs interior actually lives. No signal outruns C. Meaning moves by code reassigning what counts as where, when enough radiation accumulates. The vacuum's not empty in this framing either. It's the default workload. Zero-point modes hum like background processes. Boundary conditions are like configuration files. Plates, cavities, or intense fields change which modes are available and how expensive they are to excite. The Scharnhorst calculation, phase velocity nudging above C between perfectly conducting plates, reads like a corner case performance quirk that never touches the front velocity. Engineers already do the terrestrial version with metamaterials. Shape effective geometry, so waves take shorter coordinate paths while causality stays chained to C. And here's the payoff you can build around. If limits are budgets, progress looks like better scheduling. Precompute correlations with entanglement so the classical sidecar has less to do. Compress paths with geometry inside devices so you waste fewer ticks. Tune environments so the default workload stops eating your margin. The wall for controllable messages doesn't move. Your experience of cost does. That's not poetry, it's a design spec. One last human beat before we move on. A young team prototypes an analog horizon in a Bose-Einstein condensate and watches correlated excitations pop in pairs. Someone whispers, "It's just noise, right?" And another replies, "It's noise with a spectrum we asked for." On a whiteboard, someone writes, C equals bandwidth for action, entanglement equals structure for meaning. They underline action and meaning, not because they're soft words, but because they finally map to knobs you can turn without lying to physics or to people. Where theories collide, black holes, firewalls, and horizons. While we've been talking about budgets and refresh rates, horizons have been enforcing them with no room for negotiation. Stakes first. If quantum mechanics keeps information and general relativity keeps free fall boring at the horizon, then both can't stay naive. Unitarity says the book is never lost. Equivalence says you won't feel a wall crossing the line. Black holes made those promises collide. Start with the classic arc. A star collapses, curvature steepens, an event horizon forms the boundary beyond which no message escapes. Stephen Hawking adds heat to the picture in the 197s. Quantum fields around the horizon radiate, pairs fluctuate, one partner falls, the other escapes. The black hole glows with a temperature set by surface gravity and slowly evaporates. The outgoing radiation looks thermal. Toss in a diary, wait eons, and what you get back reads like noise. If the hole vanishes, where did the diary's information go? For a while, the answer was a shrug wrapped in paradox. Then hints accumulated. Don Page calculated how the entropy of the radiation should evolve if unitarity holds. The Page curve rises at first, then turns over halfway through evaporation as correlations start to leak out. Holography raised the hint to a principle. In certain spacetimes, a quantum theory on a boundary encodes the entire bulk, horizon and all. If the boundary is unitary, so is the bulk. Information can't vanish. It has to be encoded in the radiation somehow, even if locally the horizon feels bland. Human beats kept the math honest. After a seminar, someone wipes chalk dust off a sleeve and admits they haven't slept well since reading the latest preprint. Another draws a Penrose diagram and circles the horizon like it's a crime scene. The hallway ends with coffee, not consensus. Then 2012 arrived with a jolt. The AMPS argument, Almary, Maroff, Polchinski, and Sully, took entanglement seriously enough to break something. Near the horizon, the vacuum looks calm only if outgoing modes are entangled with their infalling partners. But if information gets out, those same outgoing modes must be entangled with earlier radiation to carry the diary's details. Entanglement is monogamous. You can't max out with two different partners. Something has to give, either no drama at the horizon or unitarity. AMPS said, if you force unitarity, the horizon erupts into a firewall that incinerates anything crossing. The smooth doorway becomes a blast furnace. Impact was immediate. If firewalls are real, the equivalence principle fails at the one place we thought was boring. If they aren't, you need a mechanism that lets information out without double booking entanglement. Holography stepped back in with a refined dictionary. Using quantum extremal surfaces and what became known as the island formula, theorists computed entanglement entropy in semi-classical gravity and found Page curves that bend the right way. The trick wasn't a courier sprinting faster than light. It was redefining which region counts as outside for the purposes of reconstruction. As evaporation proceeds, an island behind the horizon is included in the radiation's entanglement wedge. The code that reconstructs the diary lives partly where naive geometry says, inside. Translated, locality stretches in a way coding theorists find familiar. The radiation doesn't carry a naked bit that left yesterday. It carries redundancy that only becomes readable after enough of it accumulates. No signal crosses a space-like gap. Causality stays chained to see meaning moves because the global state reassigns where the ledger lives. That's a render boundary move. The frame updates its asset map, while the interface for messages never breaks the budget. Skeptics weren't quiet. Words hiding work, a margin note asked next to island. Equations answered. Extremize generalized entropy over candidate surfaces. Pick the minimal one, compute. The match to unitarity wasn't hand-waving. It produced the Page curve from gravitational path integrals in toy models. You can argue about regimes and approximations. You can't dismiss the direction. Horizons enforce budgets with code, not couriers. Here, S where the computational framing earns its keep. If C is bandwidth for action and complexity is an internal clock, then a black hole is a place where the scheduler runs hot. The horizon's thermodynamics, temperature, entropy, evaporation, are the cost accounting. The firewall crisis forced us to confront just how the cost is paid, not by a forbidden superluminal message, but by encoding that makes inside versus outside a function of what you measure and when. The no-drama promise survives if you fall freely without trying to read global codes on the way down. The unitarity promise survives because the total ledger, properly defined, never loses a line. Human micro-stories kept the 30-second beat. A postdoc pointed at a curve finally turning over and clapped a hand over her mouth. Across campus, someone drew a tiny palm tree on an island in a diagram and laughed to keep from grinding their teeth. A referee returned a report that said, "Replace metaphor with mechanism," and got a new draft with both. This is the collision point our scene predicted. No faster-than-light messages appear. The wall stands. But the meaning of where at a horizon is coded in global correlations that only become accessible within the light speed budget. Render boundaries police action. Code moves meaning. If you're looking for a glitch, it's not a tier. It's a compiler warning at the hottest line of the program. The vacuum isn't empty. Casimir, virtual fields and light's medium. Between stars, we like to say there's nothing. But the nothing hums. Stakes first. If emptiness has structure, then our speed limit interacts with a medium, not the old ether, but the restless ground state of quantum fields. That means light's behavior, and even what we call empty, depends on how the vacuum is arranged. If C is bandwidth for action, the vacuum is the default workload, and boundary conditions are the settings file we rarely open. Action starts in 1948. Hendrik Casimir calculates that two uncharged parallel metal plates held micrometers apart should feel a force pulling them together. No springs, no charges, just the vacuum. The story runs like this. Electromagnetic fields in their ground state still fluctuate. Modes that fit between the plates are restricted. Outside, more modes dance freely. Fewer allowed modes inside means lower vacuum energy there. The mismatch creates pressure that nudges the plates together. Decades later, patient experiments with polished surfaces and exquisite metrology measure that force. It's tiny and real, the vacuum leaving fingerprints. Impact lands in optics and timing. If vacuum fluctuations can be shaped, then empty space has an effective refractive character you can, in principle, tune with boundaries and fields. In materials, polarization slows light. In vacuum, virtual pairs act like a faint, universal cloud. Tweak the environment and you tweak the cloud's behavior. That does not license messages faster than light. The front velocity, the earliest detectable edge tied to causal influence, stays chained to C, but phase and group velocities can wander in weird setups without breaking causality. And that's where curiosity finds traction. Complication arrives with the Scharnhorst effect. Theory suggests that between two perfectly conducting plates, the modified vacuum permits a slight increase in the phase velocity of light parallel to the plates, fractional, minuscule, buried under mountains of noise. Even if true, it doesn't move the signal front. It nudges the carrier's phase. Finite conductivity, surface roughness, temperature, and real-world geometry shave the already microscopic effect to dust. Engineers roll their eyes at headlines and reach for error budgets. Physicists underline a point. Boundary conditions matter. Human beats keep it honest. In a lab chasing Casimir forces, a researcher times experiments to avoid garbage trucks because their rumble ruins sub-nanometer stability. She polishes gold coatings, aligns interferometers, and learns the hard way that a stray hair can double the vacuum force.